All right, so this is take not the first. So we've got a little bit written in here that I didn't really feel the need to rewrite. We are dealing with section 10.3 here, our last section of the semester, which is, of course, the time when my recording device is going to go entirely wonky. But we're still dealing with hypothesis testing, and in fact, we're still dealing with hypothesis testing that has to do with the parameter mu, right? The difference this time being that we no longer have any idea what sigma is, right? And we don't have a good way to estimate it either. So, in the exact same way that we did when we were dealing with sampling distributions, in the exact same way we did when we were dealing with confidence intervals, when we move from sigma being known to being unknown, we're going to replace all of our sigmas with s's and all of our z's with t's. So our test statistic is now called t instead of z. And instead of having a sigma right here, it has an s. Otherwise, exactly the same. Right? The other important difference between sigma being known and unknown is that we need to know something about the degrees of freedom to talk about t stuff. So the degrees of freedom are going to be similar to what they were before, 1 minus, or the sample size minus 1, so 1 less than the sample size. Now, we still have the same two methods for drawing a conclusion, except for we don't have the same tables, at least in our book. We don't have the same tables to find p-values as we do for sigma being known. So if we want to do this by hand, we're going to go with rejection regions, right? If we want to do it by hand, rejection regions only. If we want to do it by calculator, right, which we go to the stats menu, then the tests menu, then the t-test is what we choose, right? We input all of our data, and we'll talk about that some more when we get to the word problem. And once you do that, it will spit out both the test statistic for you already, and it will give you the p-value. So if you want to do it via p-value, you're going to need to bring a calculator into it, at least with the tools we have at hand. If you want to do it by hand yourself, rejection regions are going to be the only method that we're going to work through here. And those work exactly the same. Left-tailed still means that the alternative hypothesis is that mu is less than something. And this statement right here is exactly what it was last section, except all of the z's have magically turned into t's. Same for right-tailed. That means that our alternative hypothesis is talking about mu being greater than some number. And we take the same one as we had for z, and we replace it with t's. Two-tailed means that our alternative hypothesis is saying that mu is not equal to something. And in that case, we again take the same thing we had last section, which is right here, and we replace all the z's with t's. So, going down here to work in our problems, well, we'll go down further. We'll just have to zoom up for the table. So here we have our first sentence. Suppose that a doctor claims that 17-year-olds have an average body temperature that is higher than the commonly accepted average human temperature of 98.6 degrees Fahrenheit. Right? So this sentence tells us actually both of our hypotheses all in one go. Right? So this is baseline. That's going to be the same every time we do it. Right? The claim that's being made, the thing that we're testing, is that something is higher than the commonly accepted thing. Right? Now, the commonly accepted, the status quo, the sort of baseline, is always going to be the number that goes into our null hypothesis. So we've got our hypothesis all figured out. So this tells us it's going to be, a right-tailed hypothesis test. We have a sample of 25 people. We have the average temperature of those 17-year-olds, so of that sample, means that it's X bar, 98.9. The standard deviation is given in the same sentence, which is how we know that it's an S. And we have that alpha is 0.1, right? So, this would be the stuff that we would plug into our calculator, right, if we wanted to do it that way. But for us, we need our test statistic, and we need T sub alpha. So our test statistic is X bar minus mu over S divided by the square root of N, which is 98.9 minus 98.6 all over 0.6 divided by the square root of 25, which when I plugged into my calculator earlier, I got 2.5. Oh, the thing that I forgot, we need to know our degrees of freedom. We're dealing with T's here, right? But that's always going to be N minus 1, so it's 24. And our calculator will probably need that as well, though it might be able to figure it out from N. I'm not entirely sure and can't check. So we also need to know T sub alpha, right? So that's going to be T sub 0.1 with degrees of freedom 24. So we go up to here. Remember, this column is degrees of freedom, so we look for 24 here. Our alpha is 0.1, so we go down from 0.1 and over from 24, and we get 1.318. Right, and our rejection region was to check whether T was greater than or equal to T sub alpha. So that's 2.5 is greater than or equal to 1.318. Turns out it is. So this tells us that we reject H naught. So we always want to interpret this. Rejecting means that we are 90% confident. Remember, we get that by taking the opposite of alpha, right? Alpha is 10%, so the rest of that is our confidence. That 17-year-olds have a higher temperature on average. Right? So, oh no, we appear to have lost a couple of letters there, but hopefully we'll be able to figure it out. Right? So, oh, and this is even one that we did before. I believe we did this in 10.1, where all we were doing was setting things up and not analyzing it, right? So if we recall from there, right? So the claim, the status quo was 7.5. If we look down here, it's just asking if it's different. So we're going to get a two-tailed test. Right. N is equal to 10. That's just directly given to us. The average thickness of the 10 pieces of gum tells us that X bar was 7.55. And standard deviation is talked about in the same sentence as the sample. So we know it's S. And we have alpha equals 0.05. Right, so our degrees of freedom are going to be 9. We can figure that out right away. We even figured out our test statistic last time. and we found that it was 1.55. Again, you can go and check back the section 10.1 video if you want to figure out where we got that. The tricky thing here is that we're now dealing with drawing a conclusion. So we need to know T sub alpha over 2, right? And you can remember that 2 only shows up when we're two-tailed, right? So that's how those are connected. So this is T sub 0.05 over 2, T sub 0.025. So we need to look for 0.025 on the top row and 9 on the left. So 9.025, we go down and over, and we get 2.262. Right. And so our rejection region rule asked whether or not the absolute value of T was greater than T sub alpha over 2. So that's going to be is 1.55 greater than or equal to, 2.262. It is not. So this tells us that we fail to reject, right? Remember, all of our rules, whether we're doing p-value or rejection regions, always tell us when we're allowed to reject. So when we get to this point where we're plugging things into an inequality, if it turns out to be not true after we plug stuff in, we fail to reject, right? And we mentioned last time that failing to reject means that there is not enough evidence to suggest that the thickness of the gum does not satisfy the manufacturer's claim. Alrighty. So, as I mentioned last time, I'm going to be trying to figure out if I can't come up with a way to record me doing some stuff on the calculator. Again, it just keeps crashing my device. So there might be another video going up after this that just talks about how to do these two types of hypothesis testing on the calculator. But there's also screenshots and stuff in your book. So you can also check out there if I don't manage to figure out a way to get it to work. Also, you can always shoot me an email or come by office hours, either virtual or in person, and we can go over how your specific calculator does it. I can walk you through as you press the buttons. Just let me know, and I hope that the rest of your semester and exams and all that goes well.